Supercapacitors may look like ordinary capacitors from the outside, but internally they operate on a completely different scale, bridging the gap between traditional capacitors and batteries. Unlike a standard capacitor that stores energy in a simple electric field between two plates, a supercapacitor, also called an ultracapacitor, stores energy through electrostatic charge separation at an extremely large surface area, often using porous carbon electrodes and an electrolyte. This concept is based on the electric double-layer principle first observed by Hermann von Helmholtz, where charges accumulate at the interface between an electrode and an electrolyte, forming two layers of opposite charge. Because the electrode surface area is microscopic and highly porous, the effective area becomes enormous, allowing capacitance values in the range of hundreds or even thousands of farads, compared to microfarads in conventional capacitors. The energy stored in a supercapacitor follows the familiar equation E equals 1/2 CV squared, which means increasing capacitance dramatically increases stored energy, even at relatively low voltages. However, unlike lithium-ion batteries, supercapacitors do not rely on slow chemical reactions. Instead, they charge and discharge almost instantly, making them ideal for applications requiring rapid energy bursts. Their internal resistance is extremely low, enabling high power density, which is why they are used in regenerative braking systems in electric vehicles, backup power supplies, industrial automation systems, and memory protection circuits. One major advantage is cycle life. While batteries may survive a few thousand cycles, supercapacitors can endure hundreds of thousands or even millions of charge-discharge cycles with minimal degradation. However, they also have limitations. Their energy density is lower than lithium-ion batteries, meaning they cannot store as much total energy for long-duration supply. They also experience higher self-discharge rates, slowly losing stored charge over time. In practical engineering design, supercapacitors are often combined with batteries in hybrid energy storage systems. Batteries handle long-term energy supply, while supercapacitors handle peak loads and transient currents. In DC systems, designers must also consider voltage balancing when multiple supercapacitors are connected in series, because uneven voltage distribution can damage cells. This is typically solved using passive balancing resistors or active balancing circuits. In modern renewable energy systems, IoT devices, smart meters, and industrial control panels, supercapacitors provide instant backup during power interruptions, ensuring system stability and data protection. They matter because, as electronics demand faster response, higher efficiency, and longer life cycle reliability, traditional batteries alone cannot meet all requirements. Supercapacitors fill that critical performance gap,